This is the screencast for section 7.3, example 7, Cavalieri's volume theorem. That's right, Cavalieri. He's an Italian mathematician. The L is pronounced like a Y. Cavalieri's volume theorem says that solids with equal altitudes, so heights, and identical cross-section areas at each height have the same volume. So if you can see here, he has a right circular cylinder and then one that's bent. But at each cross-section, as this green sheet is showing, the cross-section has the same exact area. It's just kind of moved from side to side. In other words, if I look at this right circular cylinder and I make it slanted, it's going to have the same volume. And it looks like the radius is changing, but it's not. It's just getting further away, so it looks funny, but that's what this program does. No matter how I slide it, it's going to have the same volume. Now this follows immediately from the definition of volume, because the cross-section area and the interval A to B are the same for both solids. So this process we've been using by slicing objects and adding all those slices up, doesn't matter where those slices are, as long as those slices are the same. The volume will be the same. Well, the now try problem is a writing to learn problem. It says a solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 12. So here's x equals 0, x equals 12. The cross sections by planes perpendicular to the x-axis are circular disks whose diameters run from the line y equals x over 2 to the line y equals x, as shown in the figure. So this looks cone-like. We need to explain why the solid has the same volume as a right circular cone with base radius 3 and height 12. So in other words, this one is not a right circular cone. This is a slanted circular cone. So we can use Cavalieri's theorem to state that they have the same volume. We just need to piece together the important parts. Now, Cavalieri's theorem says they have to have equal altitudes and identical cross-section areas. Okay, so let's make some statements then. I said first, the cone's diameter of its base extends from 6 to 12. In other words, the radius of the base is 3. Now I knew it extended from 6 to 12 because x over 2 at 12 is 6 and x at 12 is 12. So 6 to 12. Then I said that the distance of the base to the tip of the described cone is 12. So its altitude 0 to 12. Its height is 12. So now I showed that the cross sections of the slanted cone described here in the problem and this right circular cone have the same size cross sections at each height. They have the same altitude and the same base, and they're both shaped like a cone. Therefore, by Cavalieri's theorem, these two objects have the same value. So again, by showing the two foundations of Cavalieri's theorem, that they are equal altitudes and they have identical cross sections, I can use his theorem to then show that they have the same value.